Here are the 5.2 Notes Power Functions. This is page 2. So we are going to take a look at what happens or how we're going to graph a cubic. This one has already been factored for you. We will talk about how we figure out how to factor cubics in a couple of later sections. Just know this one has been factored for you, and some of the basics work the same way as when we graph quadratics. So let's see if we can color code here. Our zeros. Since this is already factored, our zeros are found the same way. I'm going to set each of the factors equal to 0 and solve for x. I want the x that makes it 0. It doesn't matter how many things I am multiplying. If they multiply to equal 0, that's what we're looking for. Those are our zeros. So our zeros are x equals -4, x equals -1, and x equals 3. Sorry. And just like with the quadratic, our x-intercepts are linked to our 0. So we get -4, 0, -1, 0, and 3, 0. And if you've paid close attention or if you've looked at this closely yet, you'll notice we are graphing this function right here. Okay. Our y-intercept. So our y-intercept is where our x equals 0. I can plug it in the original function. We know from the quadratic that anything that has got a 0 involved and x involved is going to just disappear. So again, our y-intercept is the constant term. Sorry, -12. Right here, 0, -12, marked for you. There really is no way without using calculus to find the relative minimum or maximum. Those we're going to read right off the graph. The relative minimum is our lowest y value. Again, it's our y value. We want to know the lowest cost. Yeah. Our relative maximum. Again, here it's this little hilltop. It's just bigger than all the y values around it. Notice this shoots off to infinity. This is definitely not the largest y value, but it's larger than everything around it. And we use this because a lot of times our model works for some data, a certain set of data. It's just not reasonable for everything. Okay, so the domain of our function may be all real values like it is with all polynomials. But that may not make sense in terms of a real world context. So for our function here, yeah, our domain is all real values. Our range, also all real values. If we have a polynomial function with odd degree, the ends of the polynomial function are going to go opposite directions. One will go to positive infinity, one will go to negative. And so we will eventually cover everything. Okay. So graphs of polynomial functions, smooth and continuous. Which means no breaks, no start or stops, no corners or cusps. So it's going to look like a quadratic. Our cubic. And honestly, Yeah, we could have a whole lot of different things going on. So here, negative x squared, we plus something. Here we've got maybe an x to the third. Well, yeah. And then here, 1, 2, 3, 4, 5, 6, 7 changes, x to the 7-ish. So we've got a whole number of positive coefficients. You guys, these are parent function-ish. This is not all pieces, given that I drew these imaginary graphs without any kind of coordinate grid. Okay. Non-polynomial functions. Our absolute value is not a polynomial function, right? Because it has what's called a corner here, not smooth. Yeah. Anything that breaks not continuous. And as we move into rational functions, the end of this section, anything that's got an asymptote somewhere, a vertical asymptote, excuse me, not continuous. I'm done. You are welcome to stop this whenever you feel like it.